Okay, this is waves 2, grade 11. In this section, we're going to take this concept of diffraction a little bit further. Okay, but just before we do, let's just have a look here. All right, they say that the degree of diffraction is proportional to lambda over W, okay, where lambda is obviously the wavelength and W is the opening width. All right. Sometimes you'll see that as D, the aperture width, right? What does this mean? Okay. Well, it's actually simple. Right? What it means is that the amount that we bend, right, is inversely proportional to the opening width, right? What does that mean? The more the bend, inversely proportional, one goes up, one goes down. So the more the diffraction, let's say diffraction goes up, the less W must go, right? They are inversely proportional to each other. Okay? The greatest, obviously, is when we get this diffraction, the width and the diffraction, okay, linked to each other. We'll get to that in a second. And the degree of diffraction is also proportional to the wavelength, right? Which is obviously pretty obvious. Now, you know that you could create a proportionality constant there, and you could say that the degree of diffraction is equal to K lambda over W. Okay? We could say that, okay? Which is fine. We're not going to use that currently, okay? We're not going to be doing diffraction gratings. That we'll do in a separate session that I'll add in, just to flesh this out a bit more at this stage than it actually is currently, right? But what is, so what, you say? Well, let's take this situation now, right? We have said, yes, we know that diffraction, let's look at the definition of diffraction, right? And there's many. Diffraction is the ability of wavefronts to bend around small objects or spread out when they pass through a small aperture, okay? The ability of wavefronts to bend around small objects or spread out when they pass through a small aperture. Okay? Well, that's pretty straightforward. Now, let's just go back to our two, just to recap these guys over here, our two coherent sources of thingy, and let us put this one here. There's the next wavefront. There's the next wavefront. There's the next wavefront. Let's put in the other one. Okay, I'm going to try and keep them similar. Okay. Right, now let's just change the color because I want to use a different color now. You can see we are starting, our waves are going out like that, right? They are spreading out as ripples. Well, can you see that this line I've drawn here, okay, these are our crests, aren't they? This is a crest, crest, that's a crest, that's a crest, right? So if you look carefully at this, and I'm only going to use a few places, look here. At that point there, we've got a crest and a crest going together, haven't we? There it is. There's a crest, there's another one, right? There's a crest, crest, crest. But in the middle of the waves, okay, right over here, for example, can you see that there's a trough from there and a trough from the other side? So we've got places where we've got crests meeting crests and troughs meeting troughs. So what happens at that place? Well, this principle of superposition of waves tells us that if a crest meets a crest, then we get double. Because these waves are the same, we get double the amplitude of the wave, right? So at that point over there, let us call this point, let's just switch it back to black so that we can see better. Let's call this at point A, and let's call this at point B. So let's say at point A, we've got crest plus crest, so we've got double wave. Double height, right? Amplitude, actually, right? At point B, we've got trough plus trough, so we've got what? Double depth. Okay? So what have we done? The water there is going up and down double what it should, right? It's going up and down double what we normally see it as, right? Now, similarly, there are other places on this. There's a place that we're going to isolate now. I want it in blue. There's a place here. Can you see here? This is point C. There's a crest and a trough, right? Over here is a crest and a trough, isn't it? There it is. So in the middle, there's places like at point C where we've got a crest plus a trough. What have we got? We've got no movement, right? I guess back to our equilibrium thing. Well, therefore, in this water mass, we've got places that are going up double and down double, and places where there's nothing. Okay? If you actually put a light above it and took a photograph of it, you would actually see them where you've got places where you've got constructive interference and places where you've got destructive, where you've got a crest and a trough. So what have we got here? We have got over here, we've got constructive interference, and here, destructive. That's what's happening. Constructive and destructive interference. Right. Now, therefore, this tank is a bit schizophrenic if you think about it, because there's places where it's going up and down madly and places where it's still water. So let's just go back. If you, for example, were at point C over here, okay? If you're at point C, we said it's destructive, no move, and you're sitting in a boat, you are going to be sitting dead still. Whereas, if you were sitting at point A or point B, you're going to be bouncing up and down like you're in a milkshake maker. You're seriously going to get bounced up and down. Because at that point, you've got constructive interference. Okay? Now, what does it mean when we say 2 points are in phase or out of phase? In phase means that it goes up at the same time as the other point goes up. Let's say that it's in phase. Out of phase is when one goes up, the other goes down. So you can see that the constructive interference is when they are in phase. In other words, when crest and crest meet, or when trough and trough meet. Those two waves are exactly in phase. Out of phase is where they meet like that and cancel out and we have nothing. So they are totally out of phase. So waves that, for example, are at the crest and crest, constructive, they are in phase with each other. Okay? The ones that aren't are out of phase. Well, what does that actually mean then? Okay? It means that where we get this, there must be a relationship between the wavelengths, surely? Well, there is, right? If they're in phase, obviously, the two wavelengths are in phase, isn't it? If they're out of phase, then when this one is up, the other one is down. It's kind of like it's antimatter, right? Now, this interference pattern, okay, if we pass this is where we're going with this. If we pass light, okay, and there's some beautiful pictures in some of the thingies, textbooks, of what you actually get when you do this experiment. If you now take light waves, right, and you pass them through obviously a very narrow slit over there, right, because it's proportional to wavelength, so it's got to be very narrow, okay? So what do? We pass it through that. The wave that comes through on the one side and the wave that comes through on the other side are diffracted, right? So similarly, if we put a screen over here, whoops, so that's not a very neat screen at all, okay? If we put a screen up there at a known distance, all right, what do we see? Well, we see this. Let us say we shine monochromatic light, right? Just before we do that, monochromatic, that's red, blue, okay? In other words, only those that are in the spectrum, violet. So it's a single color that's coming through there, which means it's one wavelength only, okay? So it's red light or it's blue light that's going to come through here. What do we see? Well, we'll have a look now. So we'll have monochromatic blue, all right? First of all, generally, we notice that over here we get very bright. Then next to it we get dark. Then we get bright. Then we get alternating bands of bright light and dark light. What does it look like on screen actually? Well, have a look in your textbooks, but I'll try and draw it for you. It kind of looks like this, really. All right. You see over here, for example, okay, very bright, then nothing. Then bright, then nothing. Then brightness, then nothing. Then bright, then nothing. So this is our darkness and this is the light. Light, dark, light, dark, light, dark, etc. We get these bands, okay? Now, what is happening that makes it very bright? Well, what are we getting at this point here? We are obviously getting constructive interference, aren't we? Because the wavelengths are adding to increase the brightness of the light. So we're getting constructive interference at that point. So what is happening here, all right, over here, is we are getting the wavelengths in phase with each other, and they are adding. What happens in the middle? They are out of phase. They cancel each other out. Correct? The next one, they are once again in phase. They are adding to each other, right? And so we go down the loop. Right? This is called an interference pattern that we have, right? We've created, or we get an interference pattern with these alternating bright and dark bands of light, okay? What does this tell us? Well, it tells us essentially that it demonstrates that light, as we know it, is a wave, right? Now, if we go a little bit further with this, right, I'm just going to use the different colors, okay? So let me just find the middle here. Okay. Get rid of these guys, okay? Put my line back. Now, remember we said that that the diffraction, if we go back, the degree of diffraction, okay, diffraction was proportional to wavelength over W. Okay, let me just check that those were the symbols, because of course, okay, they're all different. Over there, W, I'm also just going to put, if you don't mind, I'm going to put, sometimes they use D, okay, over there as the gap, all right? it's proportional to that, right? Now, if I pass different colored lights through there, I start noticing that some colors get diffracted more than other colors, right? Well, that means there's the wavelength, because red light, okay, if you remember, red light, on the spectrum, red had the lower and blue was higher. So red has got a wavelength which is different to blue, okay? I don't have the wavelengths with me, but if you look them up, you will see that the wavelengths are different, okay? What I'll do is I'll put that into one of the exercises that we're going to do, where we put in the different wavelengths. And we're actually going to derive a formula that tells us how far these things split apart, right? Because some textbooks do it and some don't. So we're going to derive a formula. We're going to show that they diffract differently. But at this point, it's showing us really that light waves, okay, are doing exactly the same thing as physical waves in the sea. They're doing the same thing as the waves that we see generally, all right? Which means, if you like, we say that it shows us the wave nature of light, okay? If you remember from last year, you heard of the photon, right? Which showed us the particle nature of light, which gave us once again the duality of light, the dual nature of light, part particle, part wavelength, right? So when we do the examples on this section, what we're going to do is we're going to look at, or I'm going to derive the formula, and then we're going to just have a look at some of them and see the differences that happen between the red and the blue.